Hi everyone. Thank you so much for attending today's webinar on leveraging AI and satellite data for disaster response and hazard mitigation. My name is Emily Reitz. I am the Chief Technology Officer at the National States Geographic Information Council. And if you are that's a new one. If you are unfamiliar with our organization, NSGIC exists to advance effective national coordination of geospatial information by supporting state-level cooperation. We serve as a national forum for the development of capable and future-oriented geospatial leadership. And if you'd like more information on how to get involved or what we're about, you can go to our website, www.nsgic.org. And I'll put that in the chat in a second. Just a couple reminders today. Everyone's been muted on entrance, and there will be some time at the end of the presentation for Q&A. So questions can go into the chat as we're going, and they will be answered at the end. Also, a recorded version of this webinar will be made available probably about a week afterwards, so keep an eye out for an email with that. And so now I will turn it over to the presenters. Thank you so much for joining us, and hand it over to Andrew.
Hi, everyone. This is Andrew Zolli. I'm the Chief Impact Officer of Planet. If you could allow me just a moment, I'm going to pull my screen up and we'll see if we can switch over. I hope everyone can see my screen now. It's a terrific pleasure to be here with you this afternoon, and I know with a really great list of professionals who come from all across this sector and who are deeply interested in disaster response. Today, we're going to have, I think, a really terrific conversation exploring the changing landscape of disaster risks and the ways in which we're uncovering at Planet new ways that Earth observation and AI together are able to really inform the disaster risk reduction, response, recovery, and resilience cycle. Then we're going to explore some particularly new innovations. AI is used not only in the production of new kinds of insights, but in making those insights accessible in new kinds of ways. And we'll end by giving you a sneak peek at some of the ways in which these very powerful technologies are combining. With me today, as I said, I'm Andrew Zolli. I'm the Chief Impact Officer at Planet. With me is David Marvin, one of our senior product managers, one of our most important senior leaders on the product side of the organization, who will be sharing with you some really critically important new work that we've been doing around forests and forest fire risk management, et cetera. Today, I thought, so we're going to try to just go through this presentation in about 30 or 40 minutes. We have a full hour, and we'll hopefully reserve some time at the end for a robust conversation. So please do take notes, record your questions, and we'll have time to get into a more fulsome conversation toward the end. We live in a time, I think it's surprising to no one, where the disaster risk landscape itself is just being intensified and transformed in every dimension. If we just look at hurricanes and typhoons, since 1979, the number of Category 3 typhoons and hurricanes has increased in the North Atlantic has increased by roughly half every decade. And the range of those hurricanes and typhoons are actually moving northward and southward. The range of them is expanding about 60 kilometers north and south away from the equatorial regions per decade. We see more events, effectively doubling of events that are rapid intensifier storms, and we're seeing those storms therefore last longer once they make landfall. And that's just on the hurricane side. On the wildfire side, we're seeing a time of deepening, lengthening seasons of wildfire risk. We're moving from a time when we had wildfire seasons to having a permanent season across the full year. We have more fire weather days across the southeast of the United States. We're seeing increases really substantially year after year. And a push toward extremes. We've effectively seen, extreme events, the most extreme, top 0.01% of wildfire events effectively double in the first few decades of the 21st century. And that's creating a cycle of intensifying climate-linked feedback in which more carbon is burning. That carbon is having an effect atmospherically and climatologically. It's further warming and creating further drying conditions, and that in turn is creating more wildfire risk. So we're just living just across the landscape, and we could spend all kinds of time throwing statistics at you, but I think everybody here understands that the landscape is increasing in terms of its risk, and the human populations and communities that are at risk are also increasing. And you can really see that in what uh, uh, is sometimes called the expanding bullseye effect. You can take the same disaster event. In this particular diagram, what you see here is this black diagonal line in each of these four illustrations represents the path of a tornado. If the urban community grows across the path of that tornado, by definition, more assets and more human beings and more property, more ecosystems, all of it is at risk. And so that's what we see over and over again is that as we don't need to talk about climate change, we don't need to talk about all of the other risks that sometimes get thrown into the mix. Just the growth of human populations alone is sufficient to create intensifying risks across the rest of this century. So in an environment like that, we really have this really fundamental question. We have these unprecedented challenges. They're challenges that are bigger than we have confronted before. And we've got relatively stable and in some cases shrinking resources because more and more of our resources are going into response and not risk reduction, not anticipation, but reaction. But it's also the case that we have unprecedented capabilities. And the challenge for all of us who think about the working in this sector is how we align those extraordinary new capabilities with the scale of these challenges. The challenges are bigger than most of our ability to imagine in terms of their scale. But the tools that we're seeing, particularly at the intersection of the data revolution and AI, really they're the only technologies that are moving as fast as the problem itself. And in fact, actually, in some cases, faster. And that's really promising. So we spend a lot of time at Planet thinking about how we're going to align these two particular forces, or rather align these tools to these challenges. And that really raises this sort of fundamental question for all of us. It's really the framing question that brings us to the work, which is a collective resilience challenge in an era in which we will see inevitably more intense and more severe surprises. How do we leverage our best tools to help our communities persist, recover, and flourish in an age of continuous disruption? Now, when we think about it from a systems view, we really see the disaster cycle in sort of having sort of four continuous parallel activities that are deeply interlinked. The first one is about building long-term capacity in the disaster management cycle, and that is really about rehearsal, it's about preparedness, it's about institutional health and financing, it's about the ability to think ahead. And that the capacity to keep a healthy system healthy, is one of the most important elements of the cycle. Then we see a second part of the cycle, which is about sensing emerging risks. How do we instrument systems to listen for change? Now, not every disruption and disaster pre-announces itself for sure, but the very act of listening is itself a form of adaptive capacity. It's a form of keeping the system healthy. Then we see the responses to disruption. And across the disaster cycle, the one thing we've seen is that most of the most effective responses have been what we call ad hocratic, not merely bureaucratic, by which we mean they're not, because each disaster and disruption is different from the one that preceded it in its precise contours. In addition to the kind of rehearsal and the preparedness and the pre-positioning of assets that happens when we're listening for change, the ability to unlock creative, collaborative, novel approaches in the context of standardized responses is critical. So that's really represents what we think of as a coordination problem. How do we get lots of actors who are facing a challenge that no one may have quite faced exactly in the same way before to work together with a common operating picture? And then finally, there is the long-term process of learning and transformation. When a system has shown itself to be vulnerable, how do we ensure that we go through the process of determining how to bolster its long-term resilience? Do we build back precisely what we had before? Do we decouple ourselves from a dependence on systems that have shown itself to be vulnerable? That's a long-term political, engineering, technical set of challenges. And the thing about this is that data plays a role all the way through this. Data and AI, we think, connects all of these activities to each other. There's a through line here where the ability to think about the future in powerful new ways right at the beginning, which is a slow process. It's not a rapid response process. And learning and transformation at the other end is a slow process, not a fast process. But those slow processes at the end of this diagram they contain within them two fast-moving processes. That's the process of listening and sensing emerging risks and responding to disruption. And the thing that connects them is a common picture of what's at risk. And that's really where Earth observation and AI, we think, can play a powerful role. It plays a powerful role in each one of these four areas. And we'll touch on this repeatedly as we go through today's remarks. So just to kind of dig into the details now, the whole space of Earth observation and AI is moving very dramatically. And I do want to say that we will be talking today a little bit about the work that Planet's doing in this area. By no means is this all the work that's happening, all the most important work that's happening. This is the collective work of many hands. We'll talk about our work, not primarily to sell you on it, but because it's the work we know best. So just to give you a sense of where the Earth observation space is taking us, where the geospatial space is taking us, Planet has deployed now the largest constellation of Earth observing satellites. We have three components of our constellation. The first one you can see illustrated here is a constellation of hundreds of very small satellites, which orbit the Earth in a sun-synchronous orbit pole to pole, and as the Earth turns perpendicularly underneath them, acts as a line scanner for the planet. So we are collecting every day an entire take of the Earth, the entire terrestrial landmass and near oceans of the Earth, every day at a resolution of about 3.7 meters. So that's everywhere. We're not pointing cameras anywhere from space. We're collecting the whole. And the reason we'll see that's really valuable, among many other things, is in a disaster context, it means not only do we see every natural disaster as it occurs, but we see where all the assets were the day before the disruption occurred, and we continue to observe entirely, in perpetuity. So through the recovery and resilience phases that we were talking about a few moments ago. Now we have a second group of instruments that must be pointed at the Earth. They are tasked systems. They image today at 50 centimeters per pixel, and the whole system's being upgraded to 30 centimeters per pixel. I'll just run that video again while I'm speaking. And those instruments can look not everywhere on the Earth every day, but anywhere on the Earth. And we've built an entire cloud-based infrastructure that makes all of the tasking of those tasked instruments and the availability of the passively collected global take available via rock-solid platforms and APIs so that they can be woven into mission-critical infrastructure and mission-critical workflows. So one of the benefits of being able to observe the Earth continuously on a daily basis is that we overcome the perennial problem of cloud cover. I mean, obviously, the world is very cloudy. It's covered by 30% clouds at any time, but the clouds move. And because we're getting many, many more observations of the Earth, it means we're getting much tighter time series. The temporal resolution of our successful observation is very, very high. As you can see here, we may miss one or two in the context of an event, but you will have the whole set of observations available to you. And that allows us to do things that are also incredibly valuable from a data products perspective. So what you're seeing here is a cloud-free mosaic that we composite from all of the observations made in a particular time period. So you could say over the course of a week or a month, a quarter, or a year, I'd like to take the optimal observations of a particular place. Now, those are temporally smeared, but spatially accurate. So what you're seeing here is this is a monthly base map with all the cloud cover stripped out. It's a very high recency event on which you can then overlay the real-time information that's coming in day to day. So you have a very good contextual window within which to look, and then you can zoom in on specific areas. As you can see here, you're going to see a zoom in on the creek fire in California. Now, there are other things we're able to do as well, and that is one of the most important things here as it relates to AI specifically, is that we have this very dense time series information for everywhere on the Earth going back daily for the last 8 years. And the reason that's important is because one of the most important vanguard activities that we can now undertake is the training of models to understand and classify important forms of change detection. But you can only understand what's important from a change detection perspective if you've trained models to understand what's expected. And so having this very dense time series allows us to train models that really get at fundamental baselines for activity on the Earth that allow us to identify the anomalies that in turn allow us to draw attention to the truly scarce resource, which is the human operator inside the disaster context. Let me see if I can, we'll keep going here, hopefully. Let's see. Yes, so that what you get is much more up-to-date information, far fewer information gaps, far more reliable trend lines about change at the baseline level, and the ability to really detect and capture rapid change that really matters. And that all is going to happen inside the context of AI. And I mentioned to you that we're not just putting these satellites on orbit or even collecting them at the dozens of ground stations that we operate on the Earth. It's that we then have built this cloud-based native infrastructure that allows us to pull all of the commercial data and all of the publicly available data from other instruments to produce those first order derivatives, things like base maps, and make them available as comprehensive data sets, both with our data and with data that an operations center, for instance, might upload. The ability to bring your own data is one of the central things we're engineering these platforms to do, so that you can then go in and do standardized search on data, that you can do storage of information, then analyze it, and then act upon it. And this idea of being able to build an infrastructure so that we can plug efficiently at any one of those stages into the disaster workflow of state-based agencies and the like has been a central design concern from the very beginning. So this is what we start to see at the other end of that. I just picked one event. Some of you might remember there was an absolutely monumental explosion in 2020 in Beirut, Lebanon, in the port. This was the port on July 30th. This is a high resolution 50 centimeter image. This is it just a couple of days later on the day that the event occurred. And you can see here the ability to compare and contrast is really important. And that's true for all kinds of events, including flooding events. This one happens to be the flooding event that ravaged Asheville, North Carolina recently. This is from September of last year. And that ability to use these kinds of instruments in parallel is important in a disaster context, so that we combine wide area monitoring, which you see here in the Palisades fire, with the ability to complement it with zoomed in 50 centimeter imagery. And you'll see what we do with some of that 50 centimeter imagery with AI. So there's all kinds of low level machine learning tools that are used to create the image processing pipelines that clean up this imagery and make it analysis ready, that make it workflow ready for you and your applications. And those include the ability to do, false color, NDVI, burn scar analyses to track changes over time. Here you're seeing some of the false color imagery from the LA County fires, the Eaton fire in particular. But then what gets particularly interesting for us is the ability to take that and to begin to do additional AI-driven analytics. So with our partners at Microsoft, we've built very powerful, extremely accurate building damage assessment tools. They are able to ingest all of that prior imagery and the real-time event imagery to identify uh, uh, damaged infrastructure in real time. And so we've now built the kind of workflows on top of that infrastructure where sometimes in a matter of, depending on the timing of events, sometime in a matter of a few hours, we can have derivative building damage assessment that is delivered to frontline responders prior to their own deployment. So just at the point where they have maybe pre-positioned assets, but not actually gone in to a disaster affected area. And you can see that here. This is one of those damaged areas. This is the Eaton fire. Again, what you're looking at is all the damaged structures. And this is a binary, but we're actually able to do it with more sophisticated degrees of variation according to various scales. And it does vary a little bit by the nature of the disaster. So it looks one way for wildfires, it looks a little bit differently for floods or for earthquakes. Here, for instance, you can see a building damage assessment we were able to do for the wildfires that ravaged Lahaina in Hawaii and delivered this information to the American Red Cross, again, just prior to deployment. So we were actually helping to guide people in the field, both civilian evacuation, disaster response and recovery activities, all from the same real-time information. Again, all driven by a machine learning model, an AI model that was pre-trained on general disasters, then trained up by individual human beings in a matter of a few minutes based on the specific ecological circumstances on the ground, and then delivering this BDA product out to the field. And we do this with real frequency. One thing I would encourage is if you're interested, you should follow us on all the social media platforms because we regularly provide this kind of information for free in some instances directly when events occur. This is just one example relatively recently from doing exactly this event when a series of tornadoes affected, an EF3 tornado affected Arkansas. And we really saw people who were on your seats, who were really, in the state level GIS offices, really appreciative of the ability to get these derivative products that are entirely AI driven. Now, we'll have much more to show you at the end about how these begin to integrate into the kinds of AI that gets a lot of attention today, which is, the sort of large language models. We'll hold that for the end. But what I'd love to do now is hand things over to my colleague, David Marvin, who will take you through some of the work specifically on fire. So David, over to you, and I'll continue to drive, David, if you just say next slide.
Sure thing. Thanks, Andrew. So as you saw, Andrew did a fantastic job kind of setting up, how Planet positions itself and its data in terms of its ability to, respond and provide useful insights around disasters. What I'm going to do is talk a bit about how we take this underlying imagery that we collect or that is collected through public missions and apply AI to it to be able to produce new derivative products for disaster and many other applications as well. Next. Just a bit about kind of, how Planet thinks about different data products. And so we have that baseline imagery from Planet or from public missions like Landsat or Sentinel. We can produce derivative, directly derivative products just by doing band indices like NDVI or others. Next. And so showing here, NDVI, it's simple to compute. Most folks, I imagine, are familiar with this type of data set, but doesn't use any particular AI or other types of modeling to produce. It's just a kind of a raster band math to make this available. But it does provide a key, piece of additional information that can be used by AI and other models to produce derivative products. So we like to use these, in combination with our underlying imagery as well. Showing here, is NDRE, which is more ag focused relative to NDVI. Next slide. And what we can do is once we kind of combine all this imagery and derivative indices into a model, we can then produce these types of derivative products that we see here. What we're showing are canopy height, above ground carbon density, and canopy cover. These are quantitative estimates for each pixel across the landscape where you have trees the height of the trees, the amount of carbon that's contained in the landscape, and the amount of canopy cover that it contains. So truly just a type of product you cannot get by just looking at the imagery visually or looking at an index, based off the imagery. You have to kind of run it through these AI systems to be able to produce this type of insight. We provide this globally, anywhere there is forest or forest can grow, and we update it on a quarterly basis. It's at 3-meter resolution, so nearly tree scale. So it's truly a fundamentally different type of product than what's been out there in the past, and can be used as kind of both pre and post disaster to understand the changes across landscapes. Next. There's a little slow transition there. So then just kind of showing kind of the pre-post of what this looks like. Here we're showing an image in the tropics, in the Amazon rainforest. You can kind of, on the right side there, see the detail of those pre-canopies. And then next. Showing what that then looks like when we apply our AI model to produce this above ground carbon density. And as I mentioned, this works anywhere in the world. This is a nice, really just rich example from the tropics, kind of showing that landscape level detail that you can't see that right in that top image, right? We're revealing these landscape and these ecological patterns that exist across large scales, so you just cannot get with just raw imagery. Next. But we can see this really, anywhere in the world. This is a great example from Pennsylvania, just showing kind of the Appalachian mountain range and the variation in canopy cover across that region. Next. Zooming in now and looking at change over time. Andrew mentioned, kind of the key, component of our ability to track and update these data over time as a key kind of input for understanding and analyzing landscape change. Just showing kind of I think the 6-year period here, where you have a landscape in California that's an active area of forest management that undergoes a major wildfire and then gets cleared to kind of salvage log after that wildfire. Just really unprecedented detail in what we're seeing here in that change over time that you can't really get from other sources. Next slide. But then going beyond just that, forest structure and getting into applications of these data to be able to understand wildfire hazard and wildfire risk, what we can also do is produce vegetation fuels. And so beyond just can be height and cover, other aspects of the canopy and the surface, fuel loads that let you be able to produce wildfire behavior or wildfire hazard outputs. So we're showing here as an example from Orinda, California, just over the bridge in the Bay Area here, where you have kind of that satellite imagery, the parcel level data and structures. And then what Andrew just showed up here is our ability to extract out height, cover, and other fuels data sources and compare it to kind of the status quo of what's out there, which is a free resource from the US government and is kind of used in a lot of different efforts to understand fuels and wildfire hazard. But what we're able to do is produce just far higher resolution, higher quality, and update on a regular cadence those same type of data sets. Next. And we can then input this into these wildfire behavior and wildfire hazard models and produce a fundamentally different type of product and therefore insights across landscape to understand wildfire hazard. This is an annualized product that lets us understand prior to the fire season, where does that hazard exist to make decisions on where to pre-position resources, where to think about focusing efforts on defensible space and forest stand resilience. Next. Switching gears a bit to agriculture. So what we're showing here is our ability to detect boundaries of fields. Whereas prior to being able to analyze this data through an AI type of model, you have to go out and actually by hand, mark out these locations or, put GPS corner points in the field to be able to do this type of work. Now it can be done in seconds over, entire regions. Next. And then in the built environment, so moving away from ag and kind of forest landscapes, we're showing here is our ability to detect change in buildings across very large areas. And so we're zooming in here, we're showing all the locations where a change in building status, whether new one was built or old one was removed, it pops up, and then we can confirm that visually in the underlying imagery as well once that change has popped up. Next. Same thing for roads, and so we can do the change in built structures, but also where you have new roads detected Again, alerting you to where there has been changes on the landscape if you're trying to monitor a very large area. Next. And then so kind of you can take all of these data layers and begin putting them together to create additional insights, right, and applications. And so what I'm going to show here is an example for a defensible space. This is talking about the amount of vegetation near and right next to and around homes on someone's property. This is key, and especially in the Western U.S. For wildfire safety. As you reduce vegetation, nearby homes, you give your home a better chance of surviving a wildfire as it passes through, because there's less of that flammable material that can ignite and then ignite your home in turn. So there are regulations in California for this. And what we were able to do was examine all 2.5 million homes in the wildland urban interface in California and find out whether or not they were in or out of compliance with the regulations. We show that as a heat map here. Next. What we can then do is say, okay, let's look at this in more detail. We combine that information on buildings, information on property, information on vegetation and wildfire into a way to understand what's happening at the local to community scale. And so we're showing here is zooming in and showing the properties that have the highest amount of wildfire hazard and are not in compliance with the regulations, to find out where to focus efforts at that community scale to begin providing resources to those communities and to those homeowners to be able to implement better defensible space. And then you can, as I showed at the end there, look underlying what kind of vegetation is on those properties and what needs to be done to bring them into compliance. Next. Then utilities, also major kind of players in a lot of communities in terms of wildfire safety and providing them with the best available insights into the status of vegetation around their assets, particularly poles and lines. So what we can do is take our tree height layer, intersect it with the utility grid, and determine the location of all trees and vegetation that may be able to fall in and strike a tree or strike a line, causing either an outage or an ignition. So they can think from kind of top-down perspective. Next. We're going to focus their efforts where they have the highest density of these strike trees or encroachment on their lines to remove that, or to be able to put into position during high fire risk days, systems that can shut off the power or at least close the power down more rapidly when a fault is detected to reduce the likelihood of ignition. Next. Great. I'll pass it back over to Andrew. Thank you.
Okay, so thanks, David. That's great. Before we go on to the next one, I just want to pause for a second. One of the things to say is that the disaster space is so enormous, and we're talking about lots of risks, lots of hazards, different by type, different in different geographies across the United States. You're hearing us spend a little bit more time on this one around wildfires in particular, and in the Western United States, not because it's the only place we work or the only place we care about by any means, but really because it's helpful to be able to show how these things ladder up. But they're laddering up in all different ways in different places around the US. Now, the thing that I wanted to share with you is that you can see these very technical products that really are allowing us, you just think about the pieces that you've seen thus far, which is the ability to identify assets and infrastructure, the ability to see where risk is on the landscape, the ability to model interventions. These work all the way across that resilience continuum that we were discussing at the very beginning. And we are also working with all kinds of external partners and actors to work on new kinds of products that also fill important needs. And one of the most important ones is to understand where the humans are. So we spent a lot of time here talking about the risk. What you really want to see is the intersection between where risk is occurring, where impacts have occurred, and where human populations are occurring. And that's actually some work we're doing right now very closely with our colleagues at Microsoft and with a world-renowned institution at the University of Washington called IHME. What we're doing is we're providing this very high resolution imagery to our colleagues at the Microsoft AI for Good team. And what they're extracting is the world's very best, most up-to-date, world-class performing algorithms for extracting comprehensively and globally the entire built environment. So where are all the human habitats and structures, and combining our information, our data with other sources of information that allow us to get at things like um, building type, residential versus commercial, getting to some sense of utilization, looking at building heights. And then our colleagues at the University of Washington at IHME are collecting that information and combining it with all kinds of spatial demography and census information and nighttime lights and many other sources of information to get the highest resolution spatial and temporal assessments of down to about 40 meters per pixel, where in the world all the humans are. And then we're able to do that on a quarterly basis. And we'll be making these kinds of assets available essentially in those layers the layers that David was talking about and that we were mentioning a little bit earlier. So this work is currently underway. We're actually going to start an early access program for it in just next month, actually. And I wanted to give you an example. It doesn't happen to be an example from the United States, but just to give you a specific sense. We picked this because it was a community that's really disconnected. This is a little community in Ethiopia called Dolo Ado. It has never really been inventoried from this perspective. And what you see here, just to make the case, is this is the 2017 population estimate. And we happen to work with the local governments to get corroboration of this data. We know that these algorithms are very effective. Here's the same population in 2022. And the thing that's important here is not just to see where the growth is occurring. No, this is not a picture of structures. This is a population estimate in each one of those boxes of how many people we're likely to find there. The reason this is important is that this is a picture of the floodplain. And what you see in these two red circles here, this is where humanity is growing toward disaster-related, especially climate-exacerbated disaster risk in this context, where there is substantially more flooding that's been happening. And it creates the opportunity for that last category of what we think of as learning and transformation of the system. That is to say, we're not just preparing for a disaster, but we can begin to think about actually doing disaster risk reduction and shifting the baseline of risk for a whole community by creating policies that are designed to move people, and then use the same tools to determine whether or not those policies are actually being effective. So AI is all throughout this stack. But I think in particular, it's interesting that we are now thinking a lot about how these kinds of tools can show up in new ways in decision-making processes and leverage the other forms of AI that are moving, which are those large-scale generative models. So we're doing these sort of foundation models for things like population and environmental risk. And we're now thinking about and working on how we plug them in to the systems that are coming. And so we wanted to just end this set of remarks today by giving you a point of view about what's coming next. And in order to do that, I'm going to show you a little demonstration of us where we've been working very closely, in this case with Anthropic, an organization that, as you may know, produces one of those leading LLMs called Claude, to make sure that those LLMs really speak this geospatial data natively, that they understand how to interpret it and can begin to reason about it. And the reason that's important is that once we've done that, the improvements in reasoning, just generic reasoning that are happening in those models as the models get better and better, improve the ability for their ability to reason about geospatial data. And this is really the project that is really at play. And it's not just happening at Planet, it's happening across the sector. Really the rise of what we think of as sort of planetary AI, breaking down into two big buckets of activities. The first one is about classifying the world. It's about understanding where the people are, where the infrastructure and assets are, where the agriculture, water, carbon, biodiversity, but in general, where the risk is, where all of the assets are and what are the forces that are acting on them. Turning large volumes of unstructured data into really structured data sets that can then be fed laterally into these large models. And then as we do so, what we're seeing is tremendous increases in getting context and getting better reasoning about them, being able to ask questions about them in plain English, and being able to just do the very beginnings of trends and predictions. Given this pattern that you see in this time series, what is likely to be the next pattern that we see based in the sequence? But the overarching largest impact we think that's going to come from these large model integrations comes from just the context of how many people get to use them, how many people get to take advantage of geospatial data. Your kinds of insights, the kinds of technical insights that come from the people listening to this presentation, and make them available to people in plain English who may or may have a not as sophisticated, not as technical a background, but still need the information in real time on the front end. So I'm going to show you a really quick little demonstration here. And if you don't mind, just in the interest of time, I'm going to zip ahead a little bit. This is me typing in. I want to see imagery. This is one of our internal integrations with one of these LLMs. I want to see imagery from the Southern California wildfires that occurred in January 2025. Show me satellite imagery from you can see how slow I type actually, from the Santa Monica Mountains, Pasadena, and the Pacific Palisades fire. And you'll see me give it just a general range. I'm looking around the middle of January 2025, and this is the level at which I'd like you to look. I notice here I'm not saying in English, zoom out to this level. I just want you to say, zoom out far enough so that I get a good view, whatever that is. And of course, this is what we're starting to pull. You're starting to see imagery with wildfire smoke in it. That's actually what you're seeing here. And you're starting to get time series information as it's going out. It knows where all of those places are in plain English. It knows when and where to look. It's able to translate them into specific places and show you imagery from those things. Now, this is the really important part. Because we've provided lots and lots of training to the model about how to infer information from the satellite imagery, I'm now going to ask it to speculate on the origins of these fires. January seems like a strange time. It's obviously not quote unquote wildfire season. And the system says, you're absolutely right. January is an unusual time. And here are the things that were going on that are likely contributors to these kinds of events. And now give me a report that I can put in the hands of a decision maker and connect all of these dots for a decision maker. And of course, that's what comes right up. And this is, I think, really the kind of the beginning of the end of the library science era of geospatial insights for disasters. It's the beginning of the Google, Microsoft, technology for everyone moment where we're able to put these in the hands of decision makers with much greater speed. And that speed and time dimension, as everybody here on the call knows, is absolutely essential in improving our ability to reduce the effects of these events and to reduce the concurrent loss of property, suffering, and damage to the planet that comes along with them. So with that, we'll just say thank you very much for listening to us. This is just a little taste of what's to come. We're really excited to take your questions if you have them. And thank you so much for listening from both David and myself. Maybe I'll hand it back to our organizers who, and let me just say to you, please, you can ask questions of the, raise your hands or put questions in the chat. We'd love to be able to answer any of your questions if you have them.
Awesome. Yeah, thank you so much for the wonderful presentation. At this point, if anyone, just like Andrew said, has any questions, feel free either raise your hand or put them in the chat. Because I know you have questions, right? There's way too much in there to not have questions. Yes, the recording will be available later. That will go out in an email to all registrants once it is available. And I see Dean has a hand raised.
Yeah, thanks for that great overview and presentation. I was just curious if you could speak a little bit more detail how you integrate AI with the geospatial aspects of the Earth observation data or some of the features that you've loaded. Do you provide that as RAG into your analytics, or what are some of the approaches? You looked at spatial knowledge graphs. I'm just curious what kind of approaches you're taking to kind of both train and constrain the AI in terms of the geospatial data and relationships.
Yeah, I'm happy to offer. Actually, David, do you want to start with that? And I'm happy to pick up I have a few observations on that.
Sorry, I was answering a question in the chat about the wildfire hazard layer. Can you just
Sorry.
give me the quick gist of that?
Dean, do you want to ask the question again?
Yeah, I was just curious about in terms of interacting with LLMs, how do you kind of educate and constrain the LLM geospatially? Are you, you know, you just mostly like geocoding things like place names, or do you have like is there a way that you can educate the LM with geospatial, like with Earth observation imagery or spatial knowledge graphs, in
That's a great
terms of,
question. So this partnership with Anthropic is brand new, and being led by a different team within Planet. So I can't answer specifically to the demo that Andrew's showing and that kind of the approach that they're taking for the integration between Claude and our data. But in general, though, what I would I believe and I hope that we'll see coming out would be something where you can kind of integrate both an LLM and like a VLM, right? It's a visual, model, and so instead of being trained on text and video, it can be trained on, as you said, satellite imagery, right? So you take Planet's entire super deep stack of temporal and spatial imagery from its PlanetScope constellation, and train a model on top of that, right? And so you could then ask questions like, what kind of changes occurred in this part of the world, of this type, and it can basically go and source those directly from the imagery, pull that out, and you don't have to touch the rasters at all. And so that's the future we want to look towards eventually.
Yeah.
okay, great.
If I could pick up on that, Dean, it's a great question, and I just want to provide a relatively superficial answer. So one of the approaches that we take is geoencoding. We use a 700 plus vector space geoencoder with our imagery that allows us to essentially create embedding spaces that take specific advantage of Planet's precise, the imagery that we produce, the precise performance characteristics of that imagery, and to correlate it with the embedding space of LLMs, where the embedding space of the language models, we then train to correlate with the embedding spaces of the imagery. And this is very active work. So I mean, we could spend a full seminar just talking about what we're learning along the way there. But it's a combination of approaches. And part of the challenge is that we also are seeing that there's actually variability between the training sets that went into various of the other of the LLM. So their starting points are very different from each other in some cases. Almost all of them, by the way, have some geospatial awareness. There's some geospatial data that was in the training sets for almost all of the major ones from OpenAI and Google Gemini and the like, but there's real variability in the space. So we could have that conversation offline. It's a longer one than time permits today.
Yeah, I understand we can only really scratch the surface, but I guess there's aspects of individual point geolocation for people or assets and infrastructure, and then you have fields, let's say a risk area or statistical surface and things like that that are a little more involved in terms of how you model that or
100%.
ingest element.
Yeah, that's right. It's a daily conversation to determine, and it's different also just by the layers we're talking about. Actually, that's the other thing that's really important. So this is a much longer conversation, but I appreciate the question. Maybe over to Nathan.
Yes, I had yes, I had two questions. So the first question is in relation to the model you use for utility lines. Now, how accurate are those readings? And also, how can we get access to, or can we get access to that application?
So for the first part of the question, how accurate are they? So the underlying data is canopy height, and that is about 80% accurate compared to airborne lidar, which is basically you can assume the gold standard for measuring heights of vegetation. That's at a global level. And so it will vary depending on where you are regionally, but 80% is generally kind of a good number to think of. We also have compared the resulting strike tree or fallen tree layer against utility partners versions of that same data derived from airborne LiDAR. And again, we see about 85% accuracy in terms of our ability to detect these trees in the distance from lines. For accessing those data, I put this in the chat as well. For folks who are interested in any of these data layers, please reach out to sales@planet.com, and we will direct you to the right person who can handle the conversation around data access.
Thanks.
Thank you.
I also want to say I'm just going to pick a couple of questions out of the chat if that's okay. I may not get to yours, but I'm going to just start with one halfway down the list from Brandon. With so much information that can be generated for the decision makers through the use of AI, how do we ensure that AI generated information from EO data is useful rather than information overload? I really appreciate this question. And the part of the reason I picked it out slightly out of order is I actually took out, in the interest of time, a piece of our presentation, which is on this issue exactly, which I think many people here are involved in this sector know. This is dealing with the disaster cycle is dealing with both data deserts and data deluge, right? We go through periods in the cycle where suddenly we haven't historically had very much information. And then we go into environments where we could potentially have just immense amounts of information where the incremental value of each additional piece starts to diminish to zero and then actually goes negative. More information is actually harmful. One of the most powerful things about the combination of AI and EO that we see is the ability to regulate the pace of information and to integrate across many different data sets so that you get at really the fundamental question-driven, query-driven question, which is, what do I do? Like, what am I facing? What do I need? Where do I go next? Where do I pre-position assets so that I can take the most efficient path through the choice landscape? And now there's a kind of paradox there that's worth noting, which is that to keep the amount of information from either being too little or too much, but to be as informed as possible means we will have more and more and more data sets informing a sort of standardized window that's shaped by human cognition and comprehension, right? You've got lots and lots of potential information that you have to synthesize into a window so that a decision maker can say, I know what the next action is to take. In order to do that, though, the paradox is the tools are getting better than ever at being able to synthesize all of these layers and say, this is the area of greatest opportunity for action. But the chain of reasoning associated with more and more data layers means there's more and more sources of potential error. And understanding where you might have had an error in one part of a model or one part of a chain influencing another can be challenging. So part of the reason why this isn't moving even faster, I think, is because the teams are taking really great care to make sure that we understand precisely how those chains work so that we can trust the information and the guidance, just because it's so critical for these contexts. So I do want to say, I think this information regulation of the information environment is paradoxically going to be one of the greatest tools of AI, not just bringing information forward, but not bringing too much information forward. Let's see if there are other questions. Let's see. I think we answered Gwen's question. But let me just say, Gwen, you asked, since you are a commercial company, how easy it for people to get access to the data or products if they do not have good or any funding? It seems like the temporal resolution is amazing for disaster data. It is, and we do some work in this sector for free. It's worth noting we are a public benefit corporation. We have a mission to use space to help life on Earth. We, within the constraints of what we're able to do, very frequently respond to disasters and disruptions. And we were the first commercial entity ever to join the International Charter for Space and Major Disasters, which is otherwise a group of governmental bodies with space-based assets that make them available during major natural disasters around the world. We respond to dozens of events a year. We can't respond to every one, but we try really hard to provide responses when we get requests. But the major thing to say is what we see as the great opportunity is not simply the narrow, immediate response window, but it's working to instrument the entire chain of activities that happen long before, just after, and long after these events occur. Let's see if we can pick other questions out. David's answered a lot of them. Let's see. I think, David, you might have gotten all of them in the chat.
I'll just address one I picked up,
Please.
Connor. How much detail can we see in urban areas at a reasonable cost to identify mailboxes and fire hydrants programmatically and update that every day? So the highest resolution data we produce is 50 centimeter, which is probably just a bit beyond the detection of those two examples, mailboxes and fire hydrants. But for a bit larger features, cars, et cetera, and other ones that are kind of larger than half a meter in size, you could potentially train a model that could pick that up programmatically over large areas. Every day, no, the tasking system, SkySat is tasking only, where we have to point and direct and take captures from that satellite, rather than the PlanetScope constellation, which is always circling and always taking images of the Earth every day. So it'd be tough to get daily, updates, and it would definitely not be low cost to do that. So those are kind of the trade-offs that we have in different constellations.
Thanks, David. There was a question here about building damage assessment with the PlanetScope imagery, which for everyone's benefit is that daily global take at 3.7 meters, as opposed to the highest resolution. And David mentioned our higher resolution assets image at 50 centimeters. We're in the process of updating that constellation with the next generation of those instruments, which will be imaging at 30 centimeters and which have very high return rates. So they will be able to get us imagery very, very quickly. So it's not just that they're imaging at that resolution, but that they're able to offboard it to our ground stations even faster than we do today. The thing to say about that is we can do some basic building damage assessment at the PlanetScope resolution. Like anything, the model improves dramatically with increases in resolution, and the difference in resolution between the current PlanetScope and current SkySat constellation is about a factor of an order of magnitude. So the accuracy of the models goes way up, and we really try to do that at that much higher resolution. The important thing to say, though, is that often it sort of is context dependent. If you are in a moment when you have no other information, knowing where structures might be damaged, if you can get something that has significant error bars attached to it, but is better than blindness, it is really welcome. When you're actually going in and trying to understand which structures to prioritize, you really want that higher resolution asset. So we have focused most of our effort in the latter category of the highest resolution work.
I'll just do one last question to Brett. I think it's an important one for broader context here. He asked, what we require of resource managers and communicators to ensure they properly can understand AI results and accuracy and communicate the benefits of them. I actually want to flip that around. I think the requirement falls on the producers of these data and the ones who actually are building these AI models to be able to properly validate and provide public and transparent information on both how the model is trained and what the accuracy is of that model against an independent known standard. And we spent a lot of time ourselves doing this. I've linked in the chat 2 of our documentations for our forest carbon products. We're actively working on publishing this in peer-reviewed journals. I think this should be the standard for anyone working in these types of data outputs. And I think it should be incumbent upon the folks using it to understand the basics, understand kind of how these systems work, and be able to walk through and talk about them, in a really good way. But ultimately, it should fall on the producers to produce that the underlying accuracy assessments and validation.
we are at time. I want to thank everybody, especially our hosts, for inviting us in to give you this presentation today. I do want to say, just on behalf of everyone at Planet, we are a commercial enterprise. We want to be able to make sure that our products are in the hands of everybody who needs them, and that these systems are implemented, and that we're taking advantage of the best tools that we have collectively. But we are motivated by much more than that. We care about this space. We most of our work in this space is done today, because we're motivated to help reduce suffering and loss of damage, loss of property, and damage to communities and the like. So this is something we really deeply care about. We continue to work on it. We're certainly available after. We're highly Googleable. Please reach out to us if you have additional questions that we didn't get to, and we look forward to connecting with you in the time to come. So thank you again.
Thank you.